So we will talk about Friedel-Crafts alkylation and acylation today. Now let's say we have a benzene ring. And we want to form this particular compound which has a methyl group attached to it, and this compound is called toluene. Now this falls under electrophilic aromatic substitution reaction. Now this mechanism usually follows two different steps. In the first step, in this particular case, we have to find an electrophile that has a positive charge on it. So that means our electrophile in this case would be positive methyl group, and that will attach to the benzene ring. And in the second step, we have to substitute one of the hydrogens Now, when we do this reaction, we need two other reactants. Let's say we have a methyl chloride, and we have a Lewis catalyst or Lewis acid aluminum chloride. Now, Lewis acid aluminum chloride can accept electrons because it has empty orbitals. Now, let's say this is our Lewis acid, central aluminum atom and 3 chlorine atoms attached to the aluminum. Now somewhere in the space, or like in the reaction solution, we have this methyl chloride. We have this this methyl chloride, and this chlorine atom, it has, let me change the color. So it has lone pairs of electrons. Now it can donate electrons, right? Because it has lone pairs of electrons. So let's say this particular chlorine atom will try to donate electrons to this aluminum. Then it will form a complex that will look like this. So we have this aluminum, chlorine, chlorine. We had 3 chlorines. Now we are attaching this methyl chloride to it. Since chlorine already donated electrons, it has positive charge on it right now, and this aluminum accepted electrons, so now it has negative charge. Now you can also imagine this particular bond between chlorine and methyl group might break, and the electrons from the bond will be left on this positively charged chlorine atom, and you might think that the next step would be something like this, like we have this chlorine, aluminum, chlorine, chlorine, it has a negative charge on it, and then we have reformed our neutral chlorine, and somewhere in the reaction solution we have this positively charged methyl group, and now this will be our electrophile. Now the problem with this is that the stability of primary carbocation is not that great. And if you remember the stability, that tertiary carbocation is more stable than secondary carbocation, and which is more stable than primary carbocation. Now here we have a primary carbocation. And when you have a primary carbocation, it does not want to be left out in the reaction solution like this, and it has positive charge on it, and carbon doesn't like that. So we'll rather have this we'd rather have this like this. So we'll have this complex, and later on when our nucleophile will attack this, we will just simply transfer this positively charged methyl group and we'll form our aluminum tetrachloride here. This is our aluminum tetrachloride. So now that we have established that we have our complex, let's just redraw it. So we have aluminum that has 4 chlorines now and also has a methyl group, and this has a positive charge on it and this aluminum has a negative charge on it. Now this is our complex that's in the reaction solution. Now our benzene, it has higher electron density, and now that we have a strong electrophile that has a positive charge on it, or that can act as a source of this positively charged electrophile, our benzene will act as a nucleophile. So we have this benzene ring. This double bond will try to attack this methyl group here. The bond between methyl group and chlorine will break, and in the next step we'll form a benzene ring where the double bond will be broken already, and we have attached our methyl group. And just to show you that we have already a hydrogen here, right? Because this benzene ring and we have these double bonds here before, and one of the double bonds is broken, and now we have a hydrogen here. We also have hydrogens like at these points as well, because you know that's how a benzene ring works. And we also formed our aluminum tetrachloride, just like I showed before. And this aluminum still has a negative charge on it. And we have a positive charge on this benzene ring here at this carbon, because the double bond is broken and this carbon no longer has 4 bonds to it. Great. Now let's say we need a base somewhere, and that base can substitute that base can pull off this hydrogen atom. Then we can form our desired product toluene. Now we need a base, and we have this aluminum tetrachloride already in the solution, and it already has a negative charge. Now it wants to get rid of that negative charge and want to reform that aluminum chloride that we used initially, right? Our Lewis catalyst. Now let's say in the second step, so this is our first step, right? This is our first step. Now in the second step, we have, let's say, this benzene ring. We have a CH3 here, and we just drew this hydrogen like this so that we can show that how this hydrogen is removed from the benzene ring. And let's say we have this aluminum tetrachloride, and the electrons from this bond will try to take away this hydrogen, and the bond between this hydrogen and the benzene ring, or this carbon will break, and the electrons will be left within the benzene ring to reform the double bond. So in the next step, we'll form the benzene ring again. So let me draw it again. Let's say that we have our hydrogen here and we have our CH3 here, so it's kind of same. right? And we had actually the positive charge here, so I made a mistake. Anyways, so the mechanism is kind of same. So this bond will try to pull off this hydrogen away, and the bond between hydrogen and this carbon will break, and the electrons will be left here to reform the double bond. So now we reform this double bond, and we had double bonds here and here before, and hydrogen is gone now, and we have formed our toluene, and we also reformed this aluminum chloride. Now that we attached a methyl group, so this is an alkyl group, right? An alkyl group is something like, methyl, ethyl, propyl or something, and this is called Friedel-Crafts alkylation. Now the problem comes after that. Let's say that we want to attach an ethyl group. The mechanism is similar to the methyl group. But what happens when we have a propyl group? Let's say we have a propyl group. This is a propyl group. Right. And let's say we have a carbocation that has a positive charge here, right? And you want to form something like this. You want to form, so this is our benzene ring, and you want to form like this, 1, 2, 3, right? So you want to form this propyl benzene, right? That has a linear chain, So you might think, okay, the mechanism is similar, right? So you have to find a way where you have a positive charge on this propyl group. So let's say we have a positive charge here, right? So you have a positive charge here, and you can react with the benzene ring. So you have a benzene ring here. Then you say that, okay, we have this electrophile here. Now we will just form our propyl benzene. But in reality, another product also forms, which looks like this. Now, the yield in the lab in this particular case will be very less for this linear product. But you will also form some of this. But if you only want this one product, this linear one, what should you do? Well, we are coming to the next part of our video today, and which is called Friedel-Crafts acylation. But before talking about that, just to show you why we are forming this particular product, is because we have a hydride shift. As I mentioned before, that the stability of carbocation is like that, is like following, that tertiary carbocation is more stable than secondary carbocation. So that means that this tertiary carbocation is more stable than secondary carbocation, and which is more stable than our primary carbocation. Right. Now when we have something like this that has a positive charge here, so this place is like, it is our primary carbon, right? And carbon, it actually doesn't like this, and it wants to be stable, right? When it has it doesn't have these 4 bonds, it still wants to be stable somehow. Now what happens from here? So hydride shift happens, right? So that means, let's say that we have a hydrogen here, right? And that actually shifts to this particular place. Now we have this particular carbon here that has a positive charge, but this carbon is no longer this carbon has no longer the positive charge. So due to this hydride shift, so this is called hydride shift. Right, and now that we have a positive charge here, you can see that why we are forming a product like this. So the benzene attacks this particular position where it has electron deficiency. Now let's say that we have propyl chloride. Let's say we have this propyl chloride here. So this is propyl chloride, and if you react this with benzene, you'll form two different products like this. And now let's say that we have that an acyl group to it. So when we draw an acyl group to it, that means that an acyl chloride that looks something like this. Let's say that we have this right now. So this is an acid chloride, or you can also call this particular part is like the acyl part. That's why this is called acyl chloride. Now we have 1, 2, and 3 carbons, right? But we have also an acid chloride bond here. Great. Now let's say that we have this acyl chloride, and this chlorine has lone pairs of electrons. Now somewhere we also have this aluminum chloride or Lewis acid, and it can accept electrons. This chlorine will try to donate electrons here, and will also form the complex like before, where we have this aluminum, we had this chlorine, we have 3 chlorines, and we're also adding this chlorine, but now it's connected to another carbon that is connected to oxygen, and we have this. Great. Now similarly, this bond can break, and this has a positive charge right now, the chlorine atom, because it donated electrons to this aluminum and it has negative charge. Now this bond can actually break, and the electrons can be left on this positively charged chlorine atom, and what happens is that now we form an acylium ion, right? And we form this aluminum tetrachloride first, and we are also forming an acylium ion. This is called an acylium ion. Great. Now that we have an acylium ion, and this can also go into resonation, by the way. So the resonation structure would be the resonance structure would be something like this, like this particular oxygen. Let me erase this part. So this oxygen has lone pairs of electrons, right? And the oxygen can donate this electron to form a triple bond here. And so right now we have an oxygen that is positively charged because it donated electron, and we also have this triple bond between this carbon and oxygen. So this is the resonance structure, but anyways, right now we have this acylium ion, right? We have this acylium ion, and let's say this is our electrophile, and we also have benzene somewhere. So we have our benzene, that is a nucleophile, and we have this acylium ion, and this benzene ring will try to attack here, and now we are attaching this group to our benzene ring. Now this carbon, particularly this position, has a positive charge right now because it just attached our this double bond here, right? And we have this, and we had double bonds here and here. And the next step would be substituting our hydrogen. That means pulling off our hydrogen from this here. You already know that we have a hydrogen here, right? We have a hydrogen here, I'm just drawing like this, so that when another base like aluminum tetrachloride, which is already present in our reaction solution. So this bond will break, this will try to take this hydrogen away, the electrons will be left to reform the double bond here, and will form the benzene ring, which has this ketone, right now. So carbon, this particular thing is a ketone. Now that we know that we have this oxygen, now somehow if we can get rid of this oxygen, if we can get rid of this oxygen, get rid of this oxygen, we can form our linear product, the one that we wanted, this linear one, right? So propylbenzene. You can do this via Clemmensen reduction or Wolff-Kishner reaction. I will show the Clemmensen reduction and Wolff-Kishner reaction in a separate video, the mechanism and all that. But just know that, let's say that we react this in presence of zinc amalgam, so that is a mixture of zinc and mercury. So this is called zinc amalgam, so that's an alloy, and then this thing will be reduced to our linear propylbenzene. Now that we form this, so this is called Clemmensen reduction, and this is called, and this reaction is Friedel-Crafts, let me write it again, Friedel-Crafts acylation reaction. Great, I'll see you next time.